1995 and moved to Cambridge in 2005, where he was a professor of engineering and a Royal Society research professor. Then in 2018, he joined the Columbia University as a professor of neuroscience, and he was elected as a fellow of the Royal Society and has been awarded a number of prizes, including the Royal Society Failure Medal, like 2 years ago. And today he will talk about mostly the computational and experimental approaches to the human movement. So let's welcome Professor Wolpert.
Thank you. It's really great to be here. Can you hear me at the back all right? Great. So I'm going to tell you about some recent work. My lab was shut down for 2 years during the pandemic because we do human work. So we decided to focus on theory for a bit. So I'm going to tell you about that. I gave a version of this talk out of my faculty talk 2 weeks ago. And that's, as you know, as faculty, is the most scary talk you give, because you're giving it on home ground to your own faculty you're going to see every day. And at the end of it, 2 of my molecular biology friends came up to me and said, "I'm sure that was interesting, but I didn't understand anything you said." So I'm hoping not too many molecular people here, but I would really like to make this interactive. Some of the ideas are hard to get across, and they'll be different to what you're used to thinking about. So please just interrupt, and let's ask questions as we go along. The way this sort of started was the way we normally study motor learning is we bring a human or an animal into the lab, we give them a task to do, they do that task, they get better at it, and we make up a story about how they get better at that task. And I think that misses the point of what really happens in the real world. That effectively you're born, you get a stream of sensorimotor experience, and you have to learn many, many different things, for example, interact with many different tools throughout your life. And no one tells you what a task is or what a thing is. You just have to break that world down into parts. And when we begin to think about the problem of breaking the world down into separate memories, it raises a whole host of different problems, as we'll see. So today I want to talk about work primarily done by James Hield, who was a PhD in the lab and now a postdoc, in collaboration with Mate Lengel, who's from Cambridge, to talk about how do you manage a repertoire of memories. And I'm going to start by talking about context-dependent learning, both in the lab and in the wild, just to give you some overview of how we think about it. And then for the rest of the talk, I'm going to focus on a model we've developed called the COIN model, which puts contextual inference at the center of the managing the repertoire. And I'm going to talk about how the model deals with memory creation, expression updating, the distinction between proper and apparent learning, and hopefully you don't know what those mean yet, but here's a teaser. If you stay with me for 1/3 of my talk, you might know what underlines a learning curve. So when you see a curve like this, time and some performance and some task improving, we often think about that as changing some internal memory or something. And I want to try and convince you that's not the only way this can happen. That's what we call proper learning. But you can see a curve like this coming about by something we're going to call apparent learning, where there's no learning at all happening. Okay? And so I'll explain how that happens later on. And then finally, we'll look at experimental tests of the model on new and existing data. So context-dependent learning in the lab. Having written the paper about the model, we've written a couple of review papers where we try to link these ideas to different fields. And the minute you try to do that, you realize that different fields use the same word for different things and different words for the same thing. And that makes it very hard to compare. So we've tried to come up with a common vernacular in this review paper coming out soon to try and link together the different fields to think about how you manage different memories. And the critical idea is the world presents different contingencies to you. And by contingencies, I mean the statistics of the sensory cues, the states, the feedback in terms of errors or rewards, and how they depend on actions. Okay? So for example, here in a conditioning task, a contingency could be that when there's no sound, there's no shock, and when there's a sound, there's a shock. That's a fear-inducing contingency. But you can have a different contingency, one where a sound or no sound leads to no shock. That would be a fear-extinguishing contingency. So you can be in different contingencies at different times. And then what we mean by context is it's a discrete variable that controls which contingency is active. So if you're in the blue context, then this contingency is active. If you're in the red context, this contingency is active. So in a typical conditioning paradigm, you may be in the context 1 on this trial, and still in context 1 on this trial, and then maybe you go to context 2. And notice that you can vary the sensory cues. This might be one chamber, which gives you some sensory cues, and now you're in a completely different chamber for extinguishing the conditioning, and we know that you might generate 2 different memories for those 2 different sensory cues, or 2 different environments, or 2 different contexts. And you see just the same thing in episodic memory. So if you're interested in episodic memory, you may be asked to remember a series of items here in one context. For example, the background image of the pyramids, and another set of items in a different context, the background image of these temples. And we know that it's easy to recall the items in the context in which you learn them to start off with. If you're a reinforcement learning or a neuroeconomics person, again, you might have different contingencies. You might be presented with different stimuli here, little shapes. You've got a choice of which button to press, and you get a reward based on that. And maybe those contingencies change over time. And again, in this case, the background image tells you what contingency you're in. So you're in this context one, and then you go to context 2. And again, you might want to learn separate memories for these contingencies. And if you're a motor control person, as I'll talk about for most of the talk, you might want to experience different force fields. So here's a force field to the right, now you've got one to the left. And those will be different contingencies you have to learn about. Okay. So that's what happens in the lab. We sort of know what a context is in the lab, and we fool ourselves that we know what context is because we think we're controlling the context. But the critical point that that's not true in the wild. If you bring an animal or human into your lab, they've had a stream of experience before they get to you. And they're all going to be in different states before they get to you. And therefore, the way they deal with what you give them will be dependent on their previous experience. They may have generated multiple memories. Let's think about memories for objects in motor control. And once you think about they've already got multiple memories, at any point in time, you have to ask the question of which of these memories should I express or access? How do I decide what memory is appropriate? How do I decide which memories I should update of all the ones I've already developed? And how do I decide when I should use my old memories or create a new memory? And those are the 3 computational problems we're going to try and address today. And critical to this is the idea of context. The idea is context indexes a memory. That if you can say, I laid this memory down in this situation, I recognize I'm in the same situation, I can basically retrieve that memory. Okay? So estimating the context which indexes these memories is going to be critical to these 3 things. And the critical idea to get across is estimating the context is not only hard, it's uncertain. You very rarely know what situation you're in. You're in a new situation, you've got hundreds of memories. How do I know which are the appropriate memories to extract? That's a difficult problem. And as we'll see in a moment, that when you do that, you're not going to express just one memory. You may express many memories, update many memories. I have a question. Yes?
Can you talk a little bit about the spectrum of how discrete versus continuous? So on the left and right, expressing and creating are maybe more discrete. Updating is a more continuous thing, maybe?
Yeah, so expressing is choosing how much to express. We'll see in much more detail how much to express each memory. It's a weighting on each memory. Updating is again a weighting, and this is a binary thing. Either you create or you don't create. Okay? So context estimation is done. But a critical thing is that context is totally in the eye of the beholder. There's no objective measure of context. That contingencies exist. They're a physical thing in the world in some sense. But what you assign to a context, what I assign to a context, is totally subjective and depends on your brain or your animal's brain. So for example, if you're a chef and you've learnt to cut up tomatoes and apples, and for the first time you see a persimmon, you can decide to create a new memory for that, or you could decide to mix the memories from the tomato and from the apple in different weightings. It's up to you what you do with that. But effectively, you have to express your memory somehow and then update them in sensible ways. And similarly, if you're a fear conditioning person, and in the wild, this mouse comes across a ferret in a clearing in the forest, what is the context for that fearful experience? Is it that clearing in that forest, a clearing in any forest, the tree it's next to? Is it the birds singing? Is it the time of day? Is it the way the mouse got there? It's totally up to the mouse to decide what it's going to assign to context. And so context is a difficult problem to assign. Okay, for the rest of the talk I'm going to talk about motor control, but I want you to believe, or I believe, that the principles from this apply to all the domains where you want to lay down multiple memories and bring them back and update them. Okay, so let me give you an example as a British person of a sort of the way we think about context, and I think about making tea. Okay, so when I make tea, my hand is free in space, and then I interact with the kettle. And of course, when I'm interacting with the kettle, I have to change my motor commands for the properties of the kettle, and then I'm in free space again, and then I'm interacting with the teapot, and then I'm in free space again, and so on. Okay, so we can think of these as discrete switches in context. And I can label this as my green context would be my hand free in space, and the cyan context would be the hand in the kettle, and the red one that's teapot. So there are different contexts. And with each of these contexts which are changed discretely, there are states. So as I pour from the kettle, I'm changing the weight of the kettle. And as I swish the teapot about to warm it up, I'm changing the dynamics. So there are contexts which change discretely and states which change continuously. Okay? And so we're going to develop a really simple model, an abstract model of motor adaptation. There'll be no neurons in this at all. We can discuss neurons later. It's going to be simple. It's going to have scalar states, scalar observations, scaling actions. And you may say, well, that's not very impressive, and it's not very impressive, but believe me, the model's hard enough just with that. It's going to be a trial level model. It's going to be like a trial by trial thing, so it's not going to be continuous. But the core computations, I think, are applicable to more complex models of motor learning and to other forms of learning. Now, the next 3 or 4 slides are technical. If you don't follow the next 3 or 4 slides, it does not matter at all. When I come on to describe how the model works and give you examples, you won't need to know any of this, really. But there's some people in the audience, maybe like Scott, who will want to hear this, so I'm going to go over it. But I really don't think the details are absolutely vital. Some of them are. It's going to be a normative or Bayesian model, meaning we're going to explain what we think your brains and animal brains believe about the world, how the world generates data. And once we do that, then learning is inferring things we care about inside the model. Okay? So here's the generative model, the way we think the world generates data. At any point in time, this model called COIN, and we call it COIN because it stands for contextual inference and it's probabilistic, is in one context at a time. So it's in the blue context, and it stays in the blue context the next trial, and then it goes to the red context, and then the orange context. So context can change in a Markovian way across time. Okay? And then context can emit sensory cues. So you can think of this as, this is the hand free in space, how the teapot kettle, if you want to. And emit sensory cues could be the visual appearance of an object. They can or can't emit sensory cues. So maybe this is the teapot, maybe this is the cup, and so on. Critically, each context is associated with a contingency. And in the motor control, we tend to call contingency state. So this can be thought of as the weight of each object you're handling. So for example, here's the weight of the kettle, which can change over time. Here's the weight of the teapot, and so on. Okay? So we've got contexts which change discretely. We've got states which evolve over time, each one independent of the other states. And critically, when you move, the feedback you get of your action depends on the active context and its state. So here, when the blue context is active, you experience the weight of the blue object. Over here, when the red context is active, you don't experience the blue, you only experience the red. Okay, so you only experience the state associated with the active context. Okay, so that's the generative model. Now, you as a human or an animal only get to experience this bottom row. You get sensory cues and state feedback. That's all you get. You just get a stream of that across trials. And your job is to infer everything you want to know about this upper levels. And that's a hard problem for the brain. There are a lot of things you want to estimate. And so what learning is in this model is online recursive inference of all the things you care about. And let me be specific what those are. There are things which we expect to change in the model. We call those variables. And we want to estimate those. So the things we expect to change is which context is currently active? What's the current context? And because there's going to be uncertainty, what we're really going to estimate, what's the probability of every possible context I've already seen being active now? And you also want to estimate the current state of each context. I want to estimate the state of the blue context, the red, and the orange context, or the state of all the contexts I see. And I expect those 2 things to change, and I'm going to estimate them as time goes by. Then there are things which actually are fixed in the generative model, but because I'm making inferences about them, my beliefs will change over time. So they'll change in my beliefs even though they're not changing in the outside world. So for example, how many contexts are there in the world? It's probably a fixed number, but I just don't know what it is. How do contexts transition? How probable is it that the blue context will go to a red context as opposed to going to the orange context? What's the Q emission probability? How probable is it that I'll get a particular visual input given this context? And then I want to learn for each of these states how they transition. How does the blue one change over time, and how does the red one change over time? Those are things which are fixed, but I want to estimate. Okay, I'm going to go over the next 2 slides, the worst of it, and then we'll be over the worst of the maths. And in order to solve this, I have to put priors over my beliefs about all those things so that I can then do fully Bayesian normative. So I'm going to describe the priors, and then we'll be over the hump. I need a prior on the context transitions. That is, as a matrix of how context 1 might get to context 2, or context 3 and context 4, for example. And here we steal from machine learning, and we use what's called a sticky hierarchical Dirichlet process prior. It sounds horrible. The critical things about it is it's non-parametric. meaning you don't have to specify beforehand how many contexts there are in the world. The number of contexts can be infinite, and as you infer, they will grow with time as you infer more and more contexts in the world. Okay, so that's a nice feature. And the second nice feature is hierarchical, which is going to be important, meaning the way this model generates the context is it first generates the global probabilities. That is, what's my distribution of how common contexts are in general? So for example, maybe the blue is very common and the mauve, but the red one's less common. This is the distribution of how common each context is. And from that, hierarchically you generate the transitions. This is the from and to, and the length shows the probabilities. And this says, if I'm in context 1, I'm most likely to stay in the blue context, but I might go to the mauve. But the idea is this has to obey the global, such that when you update things down here, it's going to update the global, which is going to update all the others, so you get nice generalization between contexts. That's a technical thing, not important. It's also sticky in that we add sort of a diagonal element to this, so that if you're in one context, you're likely to stay in that context for a while. We also put a very similar prior on the Q emissions, that effectively there are global probabilities, maybe cups are very common and sugar bowls aren't, and then the Q emission probabilities say if I'm in a particular context, how likely is I'm going to see a cup versus a sugar bowl, for example. And that's again a hierarchical Dirichlet process with two parameters. Finally, we have to put priors on the context transitions here, and we're working very simple scalars, so we just say the state of the jth context is some retention parameter between 0 and 1, so it decays away of the previous step, and I've got some drift, and that drift allows me to maintain things over long times, and some noise. And we just put sensible Gaussian priors or truncated Gaussian priors over the A and the D. And finally, what we get as output, the state feedback, is the state of the active context plus noise. So depending on which experiment we're going to model, we have 7 or 8 parameters to fit. And I hope I'll persuade you that even with 7 or 8 parameters, we get some rich behavior to this model just from those 7 or 8 parameters. Are there any questions anyone want to ask me on the technical details? I hope the answer is no, but I'm happy to answer.
Just like, I can't fully endorse the idea that contexts are as discrete as you're treating them.
Yeah,
right?
yeah.
And when you said hierarchy, you thought, oh, maybe we're going to get.
Yeah. So no, we're not doing that here. In our Trend in Cognitive Science paper and our annual reviews neuroscience paper coming up this year, we discuss compositional context, continuous context, which would be generalizations of this. But let's see what we can get by going to discrete context in the motor domain and see how far we can get. But I absolutely agree. In the end, I think you want to be able to have compositional ones and hierarchical ones and continuous ones in different domains. I don't think we need them to explain the data I'm going to explain today. Okay. So let me just take you through the steps of the inference process, just to give you a feel for how it works, and then we'll go to a simple toy example. Okay, this is very early in learning. So in this case, this learner has just learned there's one context in the world, the blue context. And so it represents the probability of the state of that context, a true distribution over that. So it says the weight of this object has some distribution here. And it always represents the state of a novel context, a sort of a Y distribution for unknown contexts I haven't yet seen. And so from the previous trial, it's got some estimate of what context it thinks it's in. In this case, it'll think it was in the blue context, because it's only got that. It sees a sensory cue before it moves, visual appearance of an object, and it can predict now what the context it thinks it's in, given the previous context it believed, and the transitions, and the sensory cue. So these two numbers are going to be summed to 1. It's going to assign 2 numbers, 1 to each of these, which will sum to 1, because there's the only 2 options. And effectively, the right thing to do then, in terms of the belief about the state, is to mix those. So we're going to mix these 2 memories, or any memories we've got, based on this prediction. That's memory expression. So critical to here is you estimate the context before you move, and you mix all your memories to generate your motor output. You then act on the world, and you get state feedback. You may make an error, it may be heavier or lighter than you thought the object. And now you can update your beliefs based on, now you estimate your context based on the cues, but now also the feedback, and we call that responsibilities. And if it turns out that this novel context was very responsible, so you couldn't explain the data with what you've already got here, then you're going to spawn off a new memory, shown here. You'll spawn off a red memory, and then you represent that red memory thereafter. Okay? So this context estimation is also going to determine whether you generate a new memory or whether you just don't generate a new memory. And finally, we have to decide how to update all these memories based on any errors. And again, that's going to be gated by your belief that each context was responsible for that movement, memory updating. So you're going to update every memory dependent on how responsible it was. Okay? So we can see this model is going to deal with memory expression, memory creation, and memory updating within a cohesive Bayesian framework. Okay, let's get on to the fun stuff. Here is a toy example. My molecular biology friends couldn't understand that there was no data in this. There's no data in this. This is just made up data, and we're going to simulate an experiment as though we had understanding what a human or animal would do. So here is the inputs. Here is the experience of handling a bunch of identically visually looking cups, followed by a sugar bowl. And here's the weight of the cup, which you're going to experience over time. So you experience cup 1, which is light, cup 2, which is heavier, back to cup 1. You go to cup 3, which is even heavier. You empty it of water, back to cup 1. Then you go to the sugar bowl, which is a different sensory cue, but it's always the same as cup 2. Okay. Now, that's not the input we're going to give, because we have to add noise to that, because you have noise on your perception. And so we add noise to it. And what we put into the model is just these values of these purple dots, which are a noisy version, plus the discrete cue. And then we run the model with some parameters, and it just does the Bayesian inference, the learning. Okay? So the first thing it works out at each point in time is how probable is it I'm in a novel context. Now, since we start with no memories, on the very first try it goes, whoa, this is weird, and it generates a memory. But notice when it goes to cup 2, although the novel probability goes higher than 0, it doesn't get high enough to generate a new memory in this case. When you go to cup 3, though, it's unexpected and you generate a new memory for cup 3. And for this particular parameter testing, when you go to the sugar bowl, which weighs the same as cup 2, because it's got a different sensory cue, in this case, you generated a new memory. Okay? So over the course of this experiment or this experience, you've generated 3 memories for 3 different objects. And every time you generate a memory, you have to represent the full distribution of the state of that memory. And that's shown here. So what I'm showing you here is for the red, the blue, the red, and the orange memory, what the state is. So you start off with a blue memory. This isn't just a point estimate. This is a full sort of Bayesian posterior distribution. So you start off and it tracks quite faithfully cup 1. When you go to cup 2, because you didn't generate a new memory, you're going to have to update the memory for cup 1 to represent cup 2. Back to cup 1. But now when you go to the red memory, you see that you learn a new memory for cup 2, but you maintain your memory for cup 1. So now you've got 2 memories. And then finally, as a third memory comes into play here, the orange memory. So this shows you your belief about the state of the memory as you do the recursive inference through time. If you can see here, there's a sort of a grayish background. That's the prior distribution for novel contexts. Okay? So that's the internal memories you've generated. But now on every trial, you have to express those memories somehow. And so the right thing to do is to calculate this, the predicted probability, how much I believe each context is active before I move. And that's shown here. So to start off with, you express fully the blue memory. When you go to this heavy cup and you've generated this new red memory, you slowly increase your expression of the red memory and decrease your expression of the blue. And then as you go to the orange, you express the orange memory.
Sorry, can you explain what you mean by expressing a memory?
Yes, okay, so what we're going to do is we're going to weight these memories by these weighting factors. So we're going to combine here these 3 memories in proportion to these things here. So this is going to be a weighting on this. And I'm going to show you that there. So what this pink thing behind is taking the blue multiplied by this number, the red multiplied by this number, and the orange multiplied by this number, adding them together, gives me this pinkish line trace here. Okay? So it's combining them in proportion to how much you believe that they're active. Does that make sense?
I guess I'm wondering what it means. Like, what is the thing that is happening that counts as expressing a memory?
What does it happen? So you mean in the brain or in the model? So this is the weighting. Sorry?
Something you could measure, like a behavioral.
Oh, wait, this is, okay, so what you're going to measure in the end, what we get out, the motor output then, is this weighted by this, and then you take the mean. So the blue line here, for example, is what we'd get out as the behavior. So that's our output. So if we're doing an experiment, the only things we'd have access to is the experiment we give to the subject, and this blue line here would be the motor output. Okay? We have to infer what we think is happening underneath unless you're doing neurophysiology.
Presumably the decision whether or not to create a memory is some thresholded process, which is a hyperparameter that you set.
Yeah.
For the work that you're about to show us, how sensitive are those results seeing those different kinds of hyperparameters?
They're not that sensitive. I mean, they are sensitive, but they're not that sensitive. So when we fit all subjects individually, they're in parameters, okay? And we generally get the similar number of memories for experiments we're going to see. I can show you that later if you want. So it's not terribly sensitive. I mean, you can certainly go quite wide, but you can certainly go to the point where they'll generate 50 memories, which would be... Is there another question? Sorry. Any other questions? I'm not convinced I've answered your question. Yes, sorry. Got it.
So it looks like you get one shot to create a new memory when you first see cup2.
Yep.
Could you imagine sort of retrospectively after
Yes.
you handled cup2 for a while, going back and saying, I have a lot of evidence now that I should have created a memory?
We could do. We don't do that at the moment. So there are lots of things we could do. So we could do smoothing, where you do sort of replay and reevaluate and rearrange memories. We're thinking about, in this model, we never prune a memory, we never merge memories. And I think those are all things which need to happen. And maybe through sleep and replay, that's when you reorganize your memories. So, but at the moment, in this model, once it's generated a memory, it's done. If it doesn't generate it, it's done as well. But the evidence can build up. It can be that it happens the same, 'cause it's actually a probabilistic event. The probability of generating a memory is this. So it doesn't have to generate on the first trial. It can fail. And because we're doing it with particle learning, some particles have multiple, some have fewer. So we have to average.
Can you talk a little bit about the relationship between noise in this and the time scale of the update? So, like if
This noise here?
Yeah, if you're like how many steps you do, the resolution of steps relative to
The steps are at trial by trial. So the steps are on every trial. So there's no steps within a trial.
each purple dot there is a trial.
That's a trial, and then there's multiple trials here. So there was no trial. I mean, it's a trial by trial model. So there's nothing happening within a trial apart from you do this and you do this within each trial.
So, but those little pink dots,
Those pink dots are when the memories are created. Those are the trials on which memories are created.
no, the little tiny.
Oh, those are trials. Those are trials.
Yeah.
The pink dots are trials.
Right. Does that make sense?
Yeah. So this is every pink dot is a trial.
But I guess if you have more trials,
Yep.
then like what Scott was saying, you have more evidence and the noise matters less.
Yes. You could, yes.
But you
It
can imagine that like the noise that is actually there could change contextually or something.
It does. At the moment in the model, we'd assume it's fixed, the noise, and it's a parameter in the model, and you can estimate the noise. So if you have lots of noise, so we've done other experiments I won't talk about today. If you add lots of noise, then you generate fewer contexts because nothing is surprising, for example. And if you have very little noise, you're going to generate more context because things are much more distinguishable. Makes sense. Any other questions before I go on? Okay, so that's what we get as motor output. Now, but there's some interesting things in this motor output. So what you'll notice is when you come to this cup 3, you see this rather slow learning curve here, okay? And you might think, oh, what's happening here is you're slowly updating your belief about the weight of that object. But actually that's not true. In this case, on the very first trial, the weight of the object is really well represented in the state, okay? And so the weight of this object is really represented beautifully. The reason this slowly increases in your motor output is because you're very slow to believe that that context is going to hang around, okay, with this parameter setting. It takes you a long time to switch the red context on and the blue context off. So we call this apparent learning. That effectively, yes, you've learned something, but this learning curve is not because you don't know the weight of the object, it's because you're not expressing the weight. You're mixing two things you've already learned, and it's the mixing which leads to this learning curve and not the learning itself. And I'll come on to that in more detail in the next slide. In contrast, what happens here when you go to cup 2 is this really is a true change in the internal memory. And we call that proper learning. Okay? And what we're going to see later on is many phenomena in motor control we think are driven by apparent learning and not proper learning. Okay? And it's an important distinction. Finally, yes?
Sorry, this question seems more pressing than it did a second ago, so I
Over threshold.
So if I have things that I'm not thinking are different enough to create a new context
Yeah.
of memory, why don't I widen my distribution of expectations there? Why do I jump to a new value and discard the old one?
Here.
No, in the blue.
Or in the blue.
Yeah, why am I not?
Because
The world is wider than it used to be.
we don't adapt. So partly we don't adapt this parameter. You've got a fixed parameter of your noise in this model. Okay, you could do in this one. You just believe your sensory noise is somewhat fixed.
So the NIV and
Yeah, we're not varying that. And we'll talk a bit about volatility and what happens with that later. How you represent volatility, and we think of volatility more as apparent learning than real learning. But we'll see that in a moment. Okay. So finally, having made the movement, you then get the feedback, and you can estimate this responsibility, which is shown here. And then you're going to update your memories in proportion to that. So for example, when the red responsibility is very high, you're going to faithfully track here. But when the responsibility is low, you think the red's not, it's going to diffuse out. As you're not observing that object, your belief about it will diffuse out over time. Okay? So we're dealing here with memory creation, memory expression, and memory updating.
Would you just repeat your definitions of proper versus apparent learning?
I'll do it on this slide. Okay, so here are 3 learning curves. Okay, so here's the learning curves. You're learning this black thing, and here's the learning curve shown in cyan. And if I asked you which of these was proper apparent learning, you wouldn't know, specifically if you don't know what proper apparent learning are. But what I want to show you is that these are all simulations of the coin model with different parameters and different initial conditions. Okay, and so in this case, this is fully proper learning. What happened here is you came in, this fake participant, with one memory, a blue memory, for 0, and was fully expressing that blue memory. When it got this perturbation, it updated that blue memory, and that's proper learning, and express that throughout. So that's proper learning. You're changing your memory for the blue or your state of the blue. That's proper learning. In contrast, you can get the identical learning curve with a different set of parameters with fully apparent learning. So in this case, it just so happened this participant had experienced perturbations of 1s and 0 before. So it had 2 memories. Had a memory for 0 and a memory for 1. But it came into the experiment expressing fully the memory for the blue, therefore 0. When it got the perturbation for 1, all it did was change the expression. It expressed the red memory more, the blue less. The memories themselves didn't change, and that gives us cyan learning curve. Okay? So all you're doing here is mixing the memories in different proportions, and so you get the same learning curve. Here's another example. It's a mixture of proper and apparent learning. It came in with one memory, but when you got the perturbation, this participant for these parameters generated a new memory, the red one, and also changed the mixing proportions over time. So this learning comes from a mixture of the proper learning, which is this adaptation curve here, and the change in the mixing, which is the change in the expression. Does that answer your question? So by looking at just pure behavior, it's really not possible to answer the question, are you doing proper apparent or proper and apparent learning? I think there's important distinctions. I'll give you some evidence from behavioral data that we think that apparent learning is actually a big phenomena in motor control. Any questions on that? Okay, we need to get to some data now. And so I need to tell you how we capture our data for all these experiments, and we do it by having people interact with the robot. Okay, so here's a participant holding onto one of our robots, and effectively the robot can generate forces in 2 dimensions. So you can move with the robot, it can perturb your hand. We use very simple virtual reality. We have a little mirror here with a monitor facing down, so they're virtual targets in the plane, and you're able to make movements to the targets. And a typical thing we do is we can often take movements with the robot off. I'm going to call that P0, meaning a perturbation 0, there's no perturbation. And if you do that, people will make nice straight line movements. And then we can turn on different perturbations. And the typical perturbation we use is one where the force in the x and the y direction is some gain times this matrix times the velocity of your hand. And what that means is that if you make a straight line movement upwards, you get a force which is proportional to the speed of the movement to the left. It's nice, this using robots, because we don't want people to have experienced these perturbations before. We want them to be naive to these perturbations. This is unusual. This is a perturbation which is proportional to the speed. The faster you move, the bigger the perturbation, and it always acts at right angles to your current direction of motion. So very unusual. Okay? And we call that P+. And if we flip the sign here, the force acts in the other direction. We call that P-. Which one's P+ and P- is always counterbalanced in our experiments. It doesn't matter if it's left or right, but they're just opposite directions. Okay? And the way we assess learning is we could look at how far you're pushed off the path, but we don't do that for a couple of reasons. One is that's affected by how much you co-contract your arm, and we can't actually quantify how much you've learned by looking at how far you deviate. So what we do instead is occasionally, 1 in 10 trials or so, unknown to the subject, rather than apply the perturbation, we apply what's called a channel. So what we do is we basically constrain the participant's hand to a straight line to the target by a stiff one-dimensional spring. So it's a stiff spring. So from the participant's point of view, they go, wow, I did that well. But what we can do is we can measure the force they produce into the channel walls as what they anticipated the force field was going to be. So here, for example, is the force they might produce into the channel wall. And here's the force which would compensate fully for the force field. Okay, so if they produced this force, they would make a straight movement even with the force field on. And we can regress the two and say, well, that's no adaptation, that's 30%, that's 50, that's 75. So we can actually get a measure of how much adaptation we see. And so if we just put them in a P+ field for an hour, what we'll see is they slowly adapt. This is only the channel trials, and they maybe get up to 70% adaptation to the P+. Now, This sort of experiment, we just put one force field on, is not complicated enough to distinguish between any models. So we're going to have to go to more complicated paradigms to test the ideas of the coin model. So let me discuss the first paradigm. This is a paradigm called spontaneous recovery. Spontaneous recovery has been known for 100 years in conditioning. It's only recently come to the motor domain. Let me describe how it works. Participant comes in. We give them maybe 50 trials of P0, so they get to move with a robot with the forces off. Then we give them maybe 100 or so trials of P+. So we apply a force field, and this is the P+ force field. And then we briefly apply the opposite force field for a small number of trials with the aim of bringing adaptation back to 0. So they start not adapted, they adapt to this, and then they come back to 0. Okay, so that's the aim of this experiment. And then they go into a long series of channel trials where they're just constrained in a straight line and we can measure adaptation. And naively, what you might think would happen, since they're back at 0, is they produce no forces into the channel walls and they're just back at 0. But that's not what happens. If you measure adaptation during those trials, what you see is this re-expression of P+, which then decays away. Okay? So they somehow spontaneously re-express the P+. And the way this has been explained in this paper by Marie Smith is with a dual rate model. The model says that the motor output is combined of two different states, a fast and a slow state. And the fast component is going to adapt quickly, but decay quickly. And the slow is going to adapt slowly, but decay slowly. Okay? And so the output is a sum of these two, and that's shown here. So here's the fast component in green. It adapts quickly, but as the slow component takes over, it decays away. When you de-adapt, it's the fast component going negative. And so by the end of the adaptation, the fast component is negative, the slow is positive, so the sum is 0. When you go into the channel, all that happens is memories decay. And because the fast decays quickly, it re-expresses the slow component. Okay? So that's the traditional explanation. And this model, what's called the dual rate model, has become a major idea in motor control. I think it's totally wrong, as you'll see in a moment, but it's the basic fundamental idea, and people have mapped on all cognitive process to it, and I just think it's misleading. Okay, and the reason is, in this model, the fast and the slow states are always fully expressed. You just express both of them at the same time with equal weighting. Okay? So there's no concept in this model of apparent learning. It can only do proper learning. It has to adapt the internal memories and express them fully on the outside world. So let's look at this. Oh, sorry, that's what I just said there. Let's look at this paradigm simulated with the coin model. So we put in a noisy version of this into the coin model with the right number of trials. And what happens in the coin model when you run it with parameters? It starts with one memory for P0. When it sees P+, it generates a new memory for P+. And when it sees P-, it generates a third memory. So by the time you come to this channel trial phase, there are 3 memories generated. And during the channel trial phase, all that happens is the memories decay slowly back to 0 in general, or just decay to an asymptote. Here's how each memory is expressed. You express the blue memory, then you express the red, and then you express the orange memory. But critically, when you go to the channel trial phase, you start to express the red memory most, this memory here, okay? So you're getting changes in motor output here from apparent learning. In fact, you're expressing the red memory more without much changes in the memories themselves during this period. And the reason you express the red one is you've experienced this P+ the most. It's the commonest. And therefore, in the absence of any other information, you believe you're going to transition back to that context. And so when we combine this with this and look at the motor output, we get the learning, the de-adaptation, and then you get this spontaneous recovery, okay, from apparent learning. Now, a way to distinguish the dual rate versus the coin model is to change this paradigm in a very small way. So we're going to change this paradigm just with 2 trials. At the beginning of the channel trial phase, we're going to give 2 P+ trials. So having de-adapted to P-, we'll give 2 P+ trials. Now in the coin model, that's really strong evidence that that context has come back. You suddenly get the P+ context. You should now, rather than slowly re-express this, you should rapidly, what we call evoked recovery, express that. And so the prediction here is rather than the slow increase and decrease, you should rapidly increase and then decay away. Okay? So in the coin model, you can rapidly change your motor output from re-expression of memory. You don't have to do proper learning, as we'll see that the dual rate model simply can't do that because it can only do proper learning. Okay, so this is the first bit of data I'm actually going to show you. This is real data from 8 subjects each on the spontaneous recovery and evoked recovery. Remember, I'm only showing you the channel trials, not the other trials. There are no channel trials during the de-adaptation phase. So we learn this we learn P+, we de-adapt. In fact, this is what happens at the end of that. You're down here, and then you show this re-expression in the channel trial phase. Here is the evoked recovery, and again, you adapt, you're down here, but then you suddenly way back up here, and then you decay away. If we fit the dual rate model to it, it does a pretty good job of spontaneous recovery. The model was created to explain this data. It does a qualitative mismatch here. In order to get from here to here in 2 trials, it has to use the fast process. But the fast process also decays away very quickly, and therefore it can't maintain that level. If we fit the coin model to it, it actually does a better job on both of them. It can explain both the evoked and the spontaneous recovery. And if you do BIC, we win hands down. So it suggests to us that actually context estimation is controlling, in this case, memory creation and expression, and it can explain spontaneous evoked recovery in a normative way. The dual rate model is just a mechanistic model of, you've got fast and slow things in the brain, therefore let's have a fast and slow thing. This can give you different time courses, but it does it through proper learning. It's not proper learning, through learning. Any questions about this? Yes, sure.
Have you ever asked your participants to estimate the number of states that they felt they experienced?
Number of?
Or context?
No, we haven't. I'm not sure people have access to context in any cognitive way, I don't think. And we'll see, if we have time, I can show you some data about implicit and explicit knowledge of these sorts of tasks, which I think relates to the coin model. But we haven't asked them. I don't think you have any awareness. You just get pushed around all over the place in these tasks. But we haven't asked.
As a simplifying description, is it fair to say that the dual rate model just has one memory state and the coin model enables multiple memory states, and that's why it's better?
Yes. I mean, the dual rate's got one. I mean, it's got one memory which has 2 components. Yeah, absolutely. Yeah, and we take into account the different degrees of freedom when we compare the models and all that. We've got more parameters.
What happens if you increase the number of P-minus trials?
Okay, well, I can tell you what happens. I can't answer that question, but I can tell you what happens if you increase P+ trials. Okay, so which is sort of equivalent. Okay, so a reviewer has been said, they said, oh, you should really do the experiment where you increase the number of P+ trials. So the standard is this here, and now we do overlearning. We add 400 trials. And it turned out that during the review process, another group did this experiment, so we didn't have to do it for a different reason. And our prediction is that although they end up at the same level here, when you look at the spontaneous recovery, we predict much more spontaneous recovery for the overlearning compared to the standard. And that's exactly what they see in the data. So this is the data. This isn't fit to this. This is just a feed-forward simulation. You can see when they overlearn in green, they show much more spontaneous recovery, which I think is interesting, suggesting is the statistics of experience. And for example, dual rate can't really explain this because if they end up at the same level, you're pretty much at the same level in terms of those 2 states. Okay, so I think the statistics of experience, I should say P0 is something special we don't understand. If I give you loads of P0, it doesn't really change this effect. There's something special about the null of nothing, which is somehow treated differently, and we don't really understand that at the moment. So the magnitude of spontaneous recovery is sensitive to the frequency of context in the environment. This is something which I think interesting, and I hope at some point to link to physiology. Memory creation happens because you can't explain the errors. But it's known that if you experience a perturbation that comes on abruptly and goes off abruptly, it's very different to a perturbation that comes on slowly and then goes off abruptly. So if you do a reach experiment with these 2, what you find is the one which goes on abruptly and then turned off abruptly decays away very quickly. If it comes on slowly, even if it reaches the same level here, it decays away slowly. Okay. Now we can run the coin model on this, and it qualitatively reproduces this behavior. Again, we're not fitting any data here, we're just using parameters from the spontaneous recovery and the other parameters I've shown you to feed forward simulate this. You can see that when you learn it quickly, it decays away quickly. Slowly, it decays away slowly. Here's what happens inside the model to explain it. When something happens abruptly, it leads to a new memory being created. So here, when it comes on abruptly, you generate a new memory. And therefore, when you go back to baseline, you can just switch back and do a parent learn to switch back to what you had before. And so you can decay away quickly. Okay. But like a boiling frog, where you slowly heat the water, errors never get very big when you gradually adapt someone. So in this case, when you gradually adapt, you don't generate a new memory. You slowly adapt your existing memory. Okay? But here's the interesting thing. When you de-adapt, that's surprising. Now you generate a new memory for the de-adapted state. But this red state's not been around very long, so it's not very probable it's going to last. And so it takes you a while to transition back to the red, so this decay is slower. Okay? So we begin to explain these things rather nicely from memory creation versus non-memory creation.
I really appreciate at the beginning how you tried to develop a language that was useful across multiple different languages. And so I'm hoping that you can, given this data, speak back to some of the fear conditioning literature, which has found something which is quite strikingly similar.
Yeah.
Neo's work.
Absolutely. No, it absolutely links back to that.
So I would just love to hear your thoughts about that.
Yep,
The
yep.
language across it.
So in our Trends in Cognitive Science, we go through the 4 domains of learning in a lot of detail, which I wasn't going to do in this talk, but absolutely. So now we can think about why is slowly de-adapting someone to a fear more important than just de-adapting them quickly. And it's because you don't want to generate this red memory here. So in this case, the blue memory is not obliterated because effectively you've generated new red memory. So if you want to get rid of fear, you have to slowly de-adapt it so that effectively the red is not created and the blue one de-adapts. So we can link that very nicely. So many of these ideas are out there. I think this model brings them all together in a cohesive package to some extent. Any other questions? Okay, so what I've dealt with so far is really memory creation and memory expression. A key idea, though, is that memory updating is important, and this is maybe the most complicated experiment. But I think it's important. If you're in a single context world, then typically, like a Kalman filter, you'll update your state estimate now based on the previous estimate of state, and the error you got plus some Kalman gain, the learning rate. Okay, so you're going to update that, and that makes sense. But when you're in a multiple context world, you now have many memories you might want to update, and life becomes a bit more complicated. So now the right thing to do is to update the jth state based on the previous of the j state, also by the error you got and the Kalman gain, but now by how responsible you think that memory was. Okay, so there's an extra parameter in there. And what this means is that you want to update all memories in proportion to how responsible you thought they were. So we're no longer going to update one memory at a time. You might have to update 10 memories or 100 memories. Now, there may be situations where your context information is 1 and everything else is 0s, in which case you can update one memory. So we're going to create a situation here where we give people confusing information about which context there is and show you at least they update 2 memories at the same time. Okay. So all memories should be updated in proportion to their responsibility. We want to create 2 contexts in your brain. Okay, that's what we're going to do. We want to create a context for this force field to the left, P+, and one for the force field to the right. And we want you to associate each of them with a different sensory cue. I'm not going to describe what the sensory cue is. Imagine it's the color of this bounding box. So when you've got this blue bounding box, you're in context 1, which is P+. When you've got the red bounding box, you're in P-. That's context 2. And so what we're hoping you're going to learn is 2 contexts, a P+ associated with Q1 and a P- associated with Q2. And we're going to randomly interleave those trials. So on every trial, you either get this or this. And we know with the sensory cue we use that you can learn it to switch between these force fields. So you're able to learn both at the same time, and you can switch between them on a trial-by-trial basis. So having got into your brain these 2 contexts, we're going to ask how much do you update your memory for one of them based on a single trial. Okay? And for that single trial, we're either going to use something you've seen before, P1+ or P2-, or we're going to confuse you a bit. We're going to give you sensory Q2 but P+, or sensory Q1 and P-, which is going to hopefully lead to an intermediate belief of which context you're in, which will lead to updating of not just one memory but both of them. That's what we're looking for. Okay? And the way we do this is we have to know how much you've updated a memory, and to do that we need to do something before and after to measure where you were before and where you were after that trial in a triplet of trials. And the way we do that is we bracket each of these exposure trials with a channel trial so we can measure what your adaptation state is before and after. But we give you one of the cues. In this case, we give you Q1. Okay? So what we're asking you to do is express what you have in your memory for context 1, learn something, and then show me what's in your memory for context 1 again. So we're assessing one of them. Now, by symmetry of the experiment, had we looked at Q2, we'd have got the reverse. So we don't actually have to do both. Everything's sort of symmetric. And we look at the change in adaptation between this and this as single trial learning for what's in context 1. And I can give you an intuition about what we expect to see. Before you move, all you see is the cue. So that's the only information you've got before you move what the force was going to be. You see you're either in the blue or the red. So your prior for being in context 1 is if I see the subscript 1, I've got a high prior for being in context 1. If I see Q2, I've got a low price. That's my belief about what context I'm in before I move. When I move, I now get the force field. I can work out the likelihood based on the force field I experienced. Well, if I experience the plus force field, it's likely I was in context 1. If I experience a negative, I've got low likelihood. And as a good Bayesian, I can combine the likelihood and prior together to give us this. This says how much should I update my memory for context 1 based on what I see. If I see something which is completely consistent with the memory 1, context 1, I should update a lot. If I see something completely inconsistent with it, I should update little. And we get intermediate updating for these. There's a reason why actually the force field is more informative than the Q, which I won't go into, and that's why this is higher in the model. It's a technical reason. When we do the experiment, this is the data. We get beautiful graded updating of context 1. Therefore, by symmetry, we'd get the opposite for context 2. We know that individuals show this. Is not this on individuals show this, but what we can't share at the moment is whether on each trial you're actually updating 2 memories or it's stochastic. You update each memory in proportion to how much you believe it's active. That we can't tell because the data is too noisy. We have to average. But it really suggests that memories are all updated in proportion to the responsibility. And we don't update one memory, we don't express one memory, we have to mix memories. Any questions on this?
So the error bars suggest that there's a significant difference in the data just only on that last p-2 column?
Here.
Yeah, so is that, how is that explained? Is it that the test subjects were they were less sure about?
I'm not sure what you're saying. You're saying this is significant from what? Sorry.
Significantly higher than you'd expect compared to the model of the same column.
Oh, okay. Yes. So this just happens to be what happens when we fit it. So I don't know why. This is just variation. I can't answer exactly why. It's noisy data. I can tell you that. Yeah. I mean, this is what comes out of the model when we fit the data. And we fit again each subject individually, and we get different parameters. And each subject behaves a bit different in this. You know how much they weight different things. Yeah. I can't. Any other questions on this?
Am I right to assume that the measures here of learning are only really valid insofar as the person does not realize that they're in a channel trial?
Yes. I mean, no. I wouldn't say that. So the way we model channel trials is there's non-observations in this. Okay, so we assume that there's no observation in a channel trial. Life becomes, we can model channel trials as observations. It just leads to many, many more memories being generated, but fundamentally, we still get similar results. So you could imagine a channel trial that I generate a force against the wall, and I go, oh, that's the strength of the force field you've just given me. It's like half the force field now, okay? In which case you're learning another force field and you generate more memories. It doesn't really change spontaneous rate recovery or anything. It just ends up with many more memories being generated. We don't know the answer to how you deal with it, whether you deal with the non-observation. It depends whether you're looking at kinematic error, in which case you're going to say, oh, there was no error, in which case it's sort of a non-observation, or you say, oh, there was a force. And I think you'd probably look at kinematic error, so it's probably a non-observation. And generally, subjects aren't really aware of channel trials. They just keep moving, and that was a good one. Yeah. And, yeah.
Can you just say again, proportional to their responsibility in generating your confidence in which context you're in?
Second.
Say all memories should be updated proportional to their responsibility.
Yeah.
So it's their responsibility for.
The responsibility is your belief after you make the movement that which context was active during the movement. So I finish the movement, and I go, do I think that was context 1 or context 2 I was in, or memory? And therefore, and if I'm not sure, if I'm absolutely sure I was in context 1, I update that a lot. If I think, well, it's 50-50, then I update them each half. Okay, so you're estimating your belief about which context was active, and because we're giving a Q conflict here, we're giving conflicting information. We're artificially putting somewhere in between. But I think in the real world, you're often in between. You don't need hundreds of memories, and something happens in the world, and you can't be sure which context you're in.
So the strength of your belief about which context you're in is the same as the degree of expression of the memory?
No, because your degree of expression is based before you make the movement. So you have to make a decision before you move how you're going to express the memories in this case. So that's based on what the context from the last and sensory cues you have. So that's the predicted probability, that's the expression. And then when you make the movement, you've got more information. Because you've actually made the movement, get more information, and that gives you the responsibility, which is updated, and that's what controls updating and also creation. Okay. There were 2 steps in each trial, before you move and after you move. And before you move, you predict and generate the movement based on that. And after, you've got more information, and then you can update and create. Okay, so we've run 40 subjects in those 2 experiments. I've talked about the spontaneous debate recovery. And now we're going to take the parameters of those individual subjects, fix them, simulate experiments, classical experiments, and just average the data. Okay, so there's no fitting in any of this now. Okay, savings is a classic thing. You learn something once, you wash it out, and you come back and do it again, you learn it faster. Okay, and traditionally people have thought, well, what happens is you've updated your learning rate the second time or something. So here's an example, just a recent one of savings. There are many examples. You do spontaneous recovery twice. You do a spontaneous recovery once, and you come back and do it again. And what you find is, this is real data, is the second time you do it in salmon, you're quicker to learn it than the first. If we run the coin model on this, it recapitulates this behavior. However, if we look at measures of learning rate, which is the Kalman gain, they're identical the first and second time. If you look at the state representations themselves, they're pretty much identical the first time, maybe a tiny difference. What's really different is that the first time or second time you see a perturbation, you're more willing to believe you're going to transition to this new perturbation. You've experienced it before, and therefore your context transition tells you it's more likely. And so the first time you see it in green, it slowly goes up. The second time it goes up rapidly. And so you're expressing the memory more compared to your baseline memory. And that's what leads to this. So it's effectively an apparent learning phenomenon. You see a similar effect in antegrade interference. So in antegrade interference, the longer you learn P+, the harder it is for you to learn P-. Okay, so in this case, you either learn P+ immediately in black, or you learn P+ after some P+. And for example, if you learn P+ for a very long time, then this shows the P- trials. It's very hard to learn. The pink one takes a long time to learn. If you learn P+ immediately in the black, you learn it really quickly. And so there's a gradation of learning curves depending on how long you learn P+. Our model recapitulates this, and again, there's no change in the learning rate, and there's really no change in the representation of P-. It's not like it takes you longer to learn the P-. What's it driven by is your belief that P- is going to hang around. The longer you experience P+, the less willing you are to believe that P- will hang around, and therefore the less you're willing to express it. So again, this is a apparent learning phenomenon. And here's one, a paper in Science which claimed that effectively volatility affects learning rates. They did a very simple experiment. They had environments which were either very volatile, so you went between P+ and P- stochastically, the probability of one of staying in the same thing. So it changes a lot. Or they had a very static environment, or stationary environment, so the probability of staying was 0.9. And so having experienced these different environments for a set of time, they then asked, how much would you learn on a single trial? So they did those triplets. They did a channel trial, a P+, a channel trial. And what they showed is the amount of single trial learning increases over time as you experience this, but it decreases over time you experience this. And they had a complicated, weird model in which they adapted the learning rate. The idea is the learning rate goes up here, the learning rate goes down here, okay? And that makes some intuitive sense. But if we run the coin model, we get qualitatively the same behavior. But critically, the learning rate in all situations doesn't change between the conditions or over time. It's absolutely rock solid, the learning rate. More than that, the amount you update the memories doesn't change at all. It's a bit complicated. It doesn't change. It changes it by the same way in all conditions. What critically changes is your belief on the triplet. It'll stay for that trial. So remember, you do a channel trial, a perturbation, a channel trial. We measure the second channel trial really as how much is to be there. And the amount of single trial learning I get depends on how much I believe that what I experience in that P+ is going to hang around for the next trial. So when I'm in this environment, I don't believe it's going to hang around. My belief that that's going to hang around is going to go down and down. It's going to change. There's no point in me expressing what I've just learned. Whereas if I'm in this environment, well, it's going to hang around, so my predict probability of that should express more. So the idea is that this is purely driven by apparent learning. My belief on the next trial, will this perturbation remain? It's nothing to do with learning rates or the internal representations.
So you gave this introduction with the teacup
Yeah.
kettle in continuous time, and I'm trying to understand
Yes.
if this is a subset of that or a different different algorithm altogether.
So the teacup was just a cartoon example. It was still trial by trial. The assumption was each trial you experience an object which looks visually identical and it's got a weight. So it wasn't continuous in time.
But I guess my question is, in in these experiments, you're explicitly giving the subject the sense that there's a trial.
Yes, I said this is all a trial-by-trial model. If we want to do a continuous model, we'd have to generalize this to continuous. That's not impossible to do, but at the moment it's a trial-by-trial, mainly because all the experiments are trial-by-trial.
So I guess my question is just, in that sort of sense of generalization, like it seems like the way in which you would discretize or like assign something to be a trial or a discrete thing to update with matters a lot, and how that's spread across time, because that affects the switching.
Well, the switching is again defined on a trial-by-trial basis. So this probability of stay is defined on a trial. It's how much I'll switch from trial to trial. So these numbers aren't in continuous time. It's certainly true. If you drew these in continuous time and chose to sample them at different things, that would be a different experiment. So this really is a trial-by-trial model, and these probabilities are, on the next trial, will I stay with the same force field? So you're absolutely right. I mean, if you drew them in continuous time and sample them, you can make this look very static or very thing. But that, yes, I agree with that.
It seems like that process is maybe involved in what you're describing here too. Like there's some recursiveness that's interesting. Like
I don't know.
How you assign a context and how you assign a time scale to the.
So here, all these, the time scale is the trial. And the way you can have things differently, you can learn different state transitions. For example, I talked about learning the retention and the drift parameters. Those parameters govern how much you think things will change from trial to trial. And in all these models, you're learning this. So I haven't shown you any details of what happens to those parameters, but they're all changing over time as you learn these things. So for example, in this case, you probably learn bigger drift because this stays around, so it's drifting up. In this case, you probably learn less drift. So there are other parameters in these models, but they're not really key to understanding the predictions of the model. The key here is when I test something on the next trial, how much I believe it's going to stay around will explain how much I'm going to express it. So I think this is all artifact of triplets, their result, and got nothing to do with changing learning rates.
I just wanted to understand in the P stay equals 0.1.
Yeah.
That means the probability of switch
0.9
is, and so are we seeing a reverse expression where you're seeing, oh, I know it's going to be the other state?
Yeah. So
is that what it means when the curve goes down?
So when the curve goes down, it means that I learn. So once you make the movement, you don't completely switch to express the other one. You just express less of this one. And so, for example, here the single trial in our model goes down to 0. You don't express it at all because you know it's not going to be around. In theirs, it got down to 0.1, so you barely express it.
But there could be a model in which I know the context is switching, so I know to.
Yes. So it turns out that the transition matrix, people are not good at learning things switched back and forwards in motor control. So if you switch force fields left, right, people don't learn that very well.
But there are, well, we can talk about it later maybe, but there are data sets where...
there are experiments in other domains where people are very good. I'm just telling you in motor control. Alternating things are rare in motor control, I would say. I think we don't, and so I think there are constraints on that transition matrix, which says, if you give people a sequence left, right, people are not good at learning that sequence with force fields, for example.
Okay. But they would be in a discrete...
In a discrete counter, button pushing, no problem at all, Yeah. Okay, I'm going to skip a few slides because I think we should come to an end. I'm probably going to skip this slide too. I want to say we know other people have done a lot on context. People like Anne Collins, people like Gershman, and we do get a lot of effort in the paper to describe the other models on where they succeed and where they fail. Saying, here are all the things I've talked about. I haven't talked about this just for time, but there are a bunch of single context models which fail, but even some of the multiple context models fail for various reasons. And some don't model state dynamics, some don't model context transitions, some have no century queues, they're not hierarchical, or they assume none of contexts are known, or particularly they only update or express a single memory. That's a very common approximation which really fails then to capture some of this, or they learn no or few parameters. So just to summarize, we think the coin model or contextual inference is a key computation. We think it's principled and comprehensive. It's taken into account all the signals you have. You can make this model way more complicated, hierarchical, compositional, continuous. It's all doable. Just we need data which needs it. And I think there is data. So we discuss in our annual reviews paper, there are data where you have continuous context, and that makes life a little harder. It unifies a whole bunch of disparate data sets. So there were a whole bunch of different models for these different things I've talked about. But now we have a rather simple 7 or 8 parameter model which can bring them all together. It makes clear the difference between apparent and proper learning, and I think that's sort of interesting and important from a neurophysiological point of view. Like, what are the basis of apparent learning and proper learning? They must have different neural substrates. And we think it's relevant to conditioning, episodic memory, economic decision making. As I mentioned, we've got the 2 reviews coming out soon, which deal with the cognitive side and the neural side of that. And I want to thank my collaborators and my funders. Thanks very much. Happy to take any more questions if there are any.
We always encourage a student to be the first one to ask at this point.
Okay.
I'm interested in understanding whether the learning rate is actually a function of like uncertainty or you're learning at the learning rate. Like, so have you tested this in which the common gain has to be different?
Other people have done that before in sort of single situations and shown yes it is. I mean, so if you make things more or less certain, the Kalman gain adapts for that. So this is sort of factoring out that feature. So we're seeing here predominantly driven by the context estimation in these sorts of experiments. But it's not to say that always volatility doesn't change the learning rate. Just I think in this particular experiment where we do triplets, it probably doesn't. There are lots of neuroeconomic decision type or reinforcement ones where it seems to affect learning rate. And there are good normative reasons for that to happen. I'm just not sure it happens in this case. So certainly we do see that.
You mentioned that when you really speed up the switches, it people end up not learning much from the experiment. Do you think that's because when you speed up the switches, it's more like noise?
Yes, I think people don't. So I think people have sticky transition matrices. They believe things are going to stick around. In the real world, in physics, you handle some object for a bit, you handle other things. The world doesn't switch left, right on you every time you move. So I think it's just you've learned over time, you don't come into this experiment naive, that things just don't switch back and forward. In the same way, for example, if I give you a red and a blue light for the 2 force fields, you can't learn to use the color of the light to switch between the force fields. I made it red and blue there, but actually that wasn't the cue we used. And I think that's because you've learned over the course of your life that the colors of the background just not informative to forces. And if you've learned that's a really unlikely cue. Whereas other cues, which really are more informative, like the orientation of an object in the hand, you've learned are informative. So I think people come in having learned the transition matrix or step-what thing. They've also learned a lot about the emission matrix, and it's hard to override that. People have shown that if you give color cues for 5 days, you can get better at it, but you have to overwrite the prior. Yeah.
I think my lab has done the oculomotor equivalent of that last experiment.
Oh, okay.
Where, the rapid switching,
Yeah.
you don't retain. So then, if you do rapid switching in the blue environment, and then you go to the pink, where it's slow.
Yeah.
There should be some prediction of how that will persist. Now you go to the slow one. How long will it take for you to start retaining the trial by trial?
Yeah. We haven't done that. I don't know it's been done. So in those experiments, there were no sensory cues. There was just the switching. So there's no cue to tell you which environment you're in. But so you give a cue to say which environment you're in?
Well, I can tell you
okay.
the thing exactly. But if you go back to that slide, so you're in the blue thing.
I need to go back a few slides. Hold on. Oh, no, it's not that. Next one. Yep. Yeah.
So basically, we had done experiments for other reasons
Yep.
where we were just trying to make a bigger eye movement smaller, bigger,
Yep.
smaller, bigger, smaller, and then we go back
Yeah.
to the pink where we wanted.
So if we went from here to here,
Yeah.
I mean, we expect with this to rise back up to here in the end. Assuming you can overwrite what you've learned here, and that's what I guess I would expect.
Is that a meta-context switch?
Yeah, I think it would be hard. Okay, so here's what I believe. I think it'll be slower than this because of your interference. You've learned the statistic, and it takes you time to wash that statistic out. So you'll need more evidence about the stability of this to override this. We haven't. We can simulate. By the way, the code for the coin is all online on a GitHub repository. It's in MATLAB. I know that's very old-fashioned, but you can run it. You can fit data to it. You can simulate it. So if you want to know what happens in this situation, you could just run the code. It's pretty good, the code. Even Scott told me he liked it. So anyway, it's there. So I don't. You could do that. I don't know quite what would happen, but it'd be simulatable. I think there's no meta in this. This is just one matrix you're learning in this. Transitions. So it's good.
I thought it was interesting that the behavior was well explained by the average output, because I could imagine situations where the average of what to do in context.
Okay.
And the average
I can answer that. Okay. So this is a particular version of the model, and we generalize it in the text paper. So this is where we assume that you've got a scalar output and you're penalizing mean squared error. Okay, so if you're doing a squared error, the right thing to do is to average them. The really correct model is the model which says the following. I have a value for every possible action. Okay, and what I'm learning is in this context, here's my value function, and here's another value function in my other, and now I mix my value functions, and then I choose the motor command, which gives me the optimal of the mixed value functions. That's the more general version, which works for everything. If you're risk neutral, that turns out to be mean squared error in this particular case. Is that fair? So you always want to mix value functions, not necessarily motor commands. That's true.
This framework would be relevant to the matching behavior as well.
Sorry?
Matching behavior, or like sort of like Trump bandit or that type of task where like the subject is not informed of the block switches, but like over like say a choice and reward results like across trials, the subject will like at some point figure out the like environment has changed and this is back. So I wonder like if this framework could be relevant to like explaining or learning that type of behavior as well.
So I think more like a reinforcement learning task. I think so. So people have looked at this sort of learning and reinforcement. So Satinder Singh did a nice mixture of Q learners, for example. So the idea is you've got a lot of model-free learners. So this is all model-based. We're learning a model of the world. But you can think about model-free and then mixing model-free learners. So we still think the contextual inference is important in that. It's just different what you're mixing now. You're mixing model-free controllers. So I think in that case, yes, I think reinforcement learning could come into this framework. You still need to know context if you've got multiple reinforcement, multiple policies, effectively, and you want to mix those policies in a sensible way. Yeah.
So in that last one being shown here, so in the real experimental trial, the probability of staying or switching is independent based on just the current time step. But the person sees different things before the single trial learning experiment. Does one that cause explain any of the variation?
Right.
And does the model capture that based on?
Okay, we haven't looked at that in detail. The experiment's more complicated than I've described. So what you actually have to do is if you just do this, for example, then this last trial, they might be very de-adapted or very adapted, depending on the experience. So what you actually do in the experiment is you do this, and then you wash it out for a while. So you want to bring them back to baseline so they're not saturated high or low. So by the time you do the single trial, they're actually back at 0. And then you do the single trial learning. And similarly, in the experiment I talked about, the memory updating, we do a similar thing. And that's why when you're de-adapting them, you'll still give them Qs1 and Q2. And that's why Q1 and Q2 are less informative than the false field, because they get paired with nulls as well. And that's why it has less effect. That's the technical reason. So we bring them back so it doesn't really, you don't want them to be, for example, here, to be fully adapted down here, they can't get any more P minus. So you de-adapt them for a while.
This was somebody else's study.
Yes, this is someone else's study. These are all other people's studies, yeah.
I have a question. What do you think are some of the most exciting or interesting potential real-world applications?
Real-world applications? Well, okay. So I can answer that because I wrote it in my grant. I may as well stand up for it now. So there are a few real-world applications. I mean, one is rehabilitation. So what often happens in rehabilitation, those who do rehabilitation, is you bring someone into the lab, put them on a treadmill, do something with a robot, and they get way better at it, and then they go out of that situation, and they're just terrible in the real world. It doesn't transfer from that situation. And we would think of that as context-dependent learning. They've learned that they're on this robotic device. That's a context which is different from the real world. So they can't transfer that knowledge. So I think what we should be thinking about is how can we blur the distinction between the rehab environment and the real world to confuse them? Could we add noise? Could we do something so that they don't generate a new memory for that, but they adapt their existing memories? So that would be a real-world application to make it generalize outside of the rehab setting, for example. That's one real-world example. Is that enough?
There's that stroke up there. So I know, like, I come from the neurostimulation world and medical devices and so on, but I'm looking at this thinking, this could be very valuable.
So you need to find ways to confuse people so they adapt existing memories rather than create new ones which are special for that environment. And maybe the situations, fear deconditioning. People are using these sorts of ideas, before we came up with them, to think about how to get rid of post-traumatic stress syndrome, to try and de-adapt slowly, so you're de-adapting the memory and not creating a new memory. So those are some of the important things.
I'd love to get your thoughts, like speculative thoughts about experiments. The types of experiments that you're showing us are very restrictive, and it's unclear what the relationship is between these very restrictive experimental settings and behaviors in the real world. It's very clear that there are expectations in the real world which bleed out into these contexts, but I'm curious, how might you begin to look at real world expectations, motor memories, etc.? What might some of those experiments look like?
Yeah, that's a good question. So James Healder's going off to do a postdoc at the Gatsby Unit in London. He really wants to generalize some of these ideas to skill learning. So I think skill learning is a much more interesting thing, something about manual dexterity now. So there's now really good data on manual dexterity. There's also this new, is it called MyoSuite, which has revealed a fully muscle neural hand model. So you can now begin to link neural stuff to really detailed simulation of the hand and get into that. And we know the hand can do amazing numbers of things. And what he's interested in is, can these sorts of ideas be applied in some kind of skill learning and continual learning, no longer trial-based. Stuff where you have to learn things in continuous time. And he's keen to do that and link it to the neural level. We're also working on the neural thing of how would you instantiate these in neural circuits. And so we have ideas on how to do that. And in fact, Krishna Shenoy's group has got some beautiful data showing when you learn opposite force fields, you expand into new directions in neural state space. And so maybe that is memory creation when you expand into unused directions. And that's an interesting idea. We have ideas where context estimation happens in the brain. There's lots of data out there. It happens everywhere. Every bit of the brain, I think, is involved in context-dependent learning. Cerebellum, basal ganglia, thalamus, prefrontal cortex.
So you said that people don't really learn when the context switches rapidly, even if you tell them explicitly which context they're going to use. Does it change their behavior at all?
They stiffen up their arm. Yeah. So there's another way you can compensate for all these things is by co-contraction. Okay, so that's a non-specific way we're not really interested. I mean, we have studied that. That's an interesting. You can co-contract, so people just stiffen up if it's going to go back and forth. They find it too hard to compensate. So basically, you have a choice to do non-specific learning like co-contraction, which reduces the perturbation effects, or you can compensate for it. And typically, at the beginning of the experiment, you will stiffen up, and then as you learn it, you reduce your stiffness and learn to compensate. Okay.
Well, let's think.
Okay. Well, it's up to you. You can stop it now if you want.
I just didn't see it. Go ahead, Tim.
Yeah.
Would it be at all relevant to try and model how this could be implemented by small populations of neurons, or would you need a full?
I don't know. So I think we're going to go with. This is a collaboration with Matthew Engel and Guillaume Monac, and they're the neural modelers. I think they're going to go for big networks. I don't know. I mean, I think the first step is, can you do the contextual inference separate from all the memory stuff? Just a circuit which does contextual inference, then a circuit which is giving contextual inference plus the memories, and then putting them together would be interesting, and then making predictions. So that's the idea, but I'm not the neural guy on this, unfortunately. Okay, thank you. Oops, we got one more question, sure.
How do you think this model would do for expert learners in talking about these force fields? And I think part of the reason people do this contraction thing is that force field is a strange thing. They're not experts.
Yeah. So we see a lot. So we haven't looked. I don't know who was an expert for force field, but what we do see is a lot of I mean, maybe I can just show you individual subject traces. I think it's quite interesting, and we haven't looked at this in a lot of detail. But I think it's something which is going to be important to look at. Let me see if I've got it here. Okay, this is individual subjects in spontaneous recovery and invoked recovery. So for example, here's a subject who shows very nice spontaneous recovery. Here's a subject who shows no spontaneous recovery, for example. And here's one who shows almost no spontaneous recovery. So, they vary in what they show, but the coin model can pretty much fit them all. So this is the coin model on the left. And you can explain about people who have got different parameters. So we've got 7 parameters to play with, and you can explain it, and you can argue whether this is good or bad. But the variation you get, you can begin to say, well, if you believe it's more noisy and may not generate 3 memories, maybe you'll generate 2 memories. Or maybe you'll generate 1 memory, or maybe you'll generate 4 memories. So it would be interesting to think about what parameters people have and what parameters make people good. There really is, in this experiment, there's no really good or bad. Whether you show spontaneous or not is just an epiphenomenon. It's not important. The original learning can vary a lot. So here's a terrible subject. It takes ages for them to learn. Okay, and here's a really brilliant subject who learns in like 2 trials. And again, we can explain that with variations in the parameters. So we could begin to look at individuals. The field has not tended to look at individual subjects. They tend to average all the data, and it just washes out the interesting variation. in this case. Okay. Okay, thank you very much. Okay.